Okay, problem 61. This problem kind of took me down a pretty deep rabbit hole. I ended up spending, I don't know, like a couple hours looking into and working out all sorts of stuff that I thought was really interesting and I kind of want to share, but I don't want this video to be like an hour long. So I'm going to make this video really geared towards just getting the answer and moving on. And then I'll make another video that gets into those interesting topics related to this problem. So anyways, for the sake of answering this question, the key fact that you'll need is that to multiply complex numbers, just add their angles and multiply their magnitudes. I'm pretty sure I've already talked about this in a previous video, but really quickly, if I have this vector in red, maybe I'll call it v, and the length of v is equal to 2. And then I have this vector u, and the length of u is equal to, I don't know, maybe 3. And I'm interested in the product of these two complex numbers that are defined by these vectors. All I have to do is figure out this angle here, and this angle here, and then add those together. I don't know, this is like 60 or so, and this is 135 or so. So their sum would be 195 or so. I don't know, maybe something like this. And then multiply their magnitudes. 2 times 3 is 6. I draw the vector with this direction and magnitude 6. That defines a complex number. This complex number is the product of these two complex numbers. That fact is useful in a wide variety of problems dealing with complex numbers, including this one here. So in this one here, what we're interested in is the sum and product of all the primitive 10th roots of unity. So what is a primitive 10th root of unity? Well, conveniently that's defined for us up here. A 10th root of unity is just a complex number, so that when we raise that complex number to the 10th power, we get 1. And that 10th root is primitive if we don't get 1 when we raise that complex number to any other integer power between 1 and 9. Let me draw a picture. Here's my coordinate plane, and here's 1. Here's a decent looking unit circle. When I take a complex number z and I raise it to the 10th power, really what I'm doing is I'm multiplying that complex number by itself 10 times. But remember, anytime we're multiplying two complex numbers, all we're really doing is adding their angles and multiplying their magnitudes. I need the product of these complex numbers to be equal to 1. In other words, this point on the complex plane. Well, because the magnitude of the vector defining this point is exactly 1, the only way I'm going to multiply a complex number by itself a bunch of times and get 1 as the answer is if the magnitude of that complex number is exactly 1. What I'm saying is z is going to have to fall somewhere on the unit circle. So far, we've just considered the fact that when we're multiplying complex numbers, we multiply their magnitudes. We also need to consider the fact that when we multiply complex numbers, we add their angles. We need to end up at this point 1, which is defined by an angle of 0. So one way we can do that is by starting out with this complex number 1. But another way we could do that is by traveling 1/10 of the way around the unit circle. Let's see, 1/10 is 36 degrees, so roughly right here. Note that if we multiplied this complex number by itself 10 times, we'd add this angle 36 degrees to itself 10 times and get 360 degrees, which would leave us coterminal with this angle of 0. Because the magnitude of this vector is 1, the product of 10 ones is just 1, so we stay on this unit circle. What I'm saying is this complex number is a 10th root of unity. Not only could I travel 1/10 of the way around the unit circle, I could travel 2/10 of the way around the unit circle. So 2 of these 36s, 72 degrees, roughly here in my picture. 10 72s gives me 720. I end up coterminal with 0. As you can probably guess, that would also be true for the complex number defined by the vector that's 3/10 of the way around the unit circle, or 4/10 of the way around the unit circle, or 5/10 of the way around the unit circle, or 6, 7, 8, or 9/10 of the way around the unit circle. These 10 complex numbers make up our 10th roots of unity. Solutions to the equation z to the 10th power equals 1. However, if you reread the problem, we're not interested in the 10th roots of unity. We're interested in the primitive 10th roots of unity. So values that satisfy this equation, but don't satisfy the equation z to the first power equals 1, so we don't want this number, or z to the second power equals 1, so we don't want this number, or z to the third, fourth, fifth, sixth, seventh, eighth, or ninth power equals 1. To make sure that we don't satisfy any of those other equations, what we need is for the fraction of the way we traveled around the circle to be relatively prime with 10. So traveling 1/10 of the way around the circle will certainly work. 2/10 of the way around the circle will not work because 2 is not relatively prime to 10. 3/10 of the way will work. 4/10 of the way will not work. 5/10 won't work. 6/10 won't work. 7/10 will work. 8/10 will not work, but 9/10 will work. We have 4 primitive 10th roots of unity at these 4 points here and here and here and here. What we're interested in is 2 things, S and P. S is the sum of these numbers, P is the product of these numbers. Let's first find S. Note that if I call this point A plus BI, then because these points have the same x coordinate, and the y coordinate of this point is the opposite of the y coordinate of this point would be A minus BI. If I call this, I don't know, C plus DI, kind of exploiting symmetry, the same logic would tell me that this point down here is C minus DI. So S would be equal to 2A plus 2C. Looks like S is a real number, which is nice. What real number is it equal to? Well, that's not immediately obvious, at least not to me, because I don't know what A plus C is equal to. Fortunately, if you look up at the answers here, the only possibilities are -1, 0, and +1. And just by inspection, I can tell that the absolute value of A is greater than the absolute value of C, right? The x coordinate here is further to the right than the x coordinate here is to the left. I don't know exactly what this x value is, but it looks like it's, I don't know, like 0.8 or something. I don't know what this x value is either, but it looks like roughly, I don't know, -0.3. If I added those up, I'd get roughly 1/2. 1/2 times 2 would give me 1. Looks like S is approximately equal to 1, but it's certainly not equal to -1 or 0, because to be equal to 0, A would have to be equal to C, and just by inspection I can tell that that's not the case. And to be negative, the absolute value of C would have to be greater than the absolute value of A, and clearly that's not the case. It turns out S is exactly equal to 1, and we can prove that if we can show that the cosine of 36 degrees plus the cosine of 3 of these 36s, in other words 108 degrees, is equal to 1/2, because the cosine of a 36-degree angle is defined to be the x-coordinate on the unit circle corresponding with this point, and the cosine of a 108-degree angle is defined to be the x-coordinate on the unit circle corresponding with this point. But I don't know the cosine of 36 and the cosine of 108 offhand, so I don't know that this is equal to 1. For the purposes of the test, it's good enough to process of elimination my way into the answer. But being the curious math nerd that I am, I kind of want to prove that this is true. I'm going to do so, but not in this video. I'm sure there's lots of different ways you can prove this fact, but I found two that were pretty interesting. One that's purely algebraic and one that's purely geometric, and found them interesting enough that I thought they deserved a video. But again, I digress. From this picture, we can tell that S is equal to 1. To answer this question, all we got to do is determine what P is equal to. Well, that's easy enough. P is just the product of these complex numbers, and we started this video talking about how we multiply complex numbers. We have to add the angles, and then we have to multiply the magnitudes. Well, the magnitudes are easy. Those are all equal to 1 because we're on the unit circle. So maybe P is the complex number defined by the vector with a magnitude of 1 times 1 times 1 times 1, in other words 1, and a direction of this angle plus this angle plus this angle plus this angle. Well, you could figure out all those angles and add them up either in radians or degrees, but you could also take advantage of some symmetry, and instead of thinking about this angle as 324 degrees, you could think about it as -36 degrees. So 36 degrees and -36 degrees gives me 0. 108 degrees and -108 degrees gives me 0. It looks like the direction of this complex number that's going to define P is just equal to 0. What is the complex number with a magnitude of 1 and a direction of 0? Well, we've seen that already. That's this point right here. It's got a real part of 1 and an imaginary part of 0. P is just equal to 1. We know P is 1, and by process of elimination, we've been able to figure out that S must be equal to 1. So the answer to the question must be E.